I think someone just joined and jumped out, so.
Jen, it's Simon here. Can I ask you or could you explain the double slit experiment from a physicist's point of view to layman?
Why not just start at the single slit?
Okay, single slit then.
Because the double slit's more difficult, I think, to understand.
Yep, all right.
So if we start at the single slit, now you have to understand the way my model explains this is not the same as how modern physics explains it. They have their own little wacky theory that I don't really buy into. So just understand that this is my theory, not mainstream theory. So basically the way it works is, do you understand the uncertainty principle?
Well, not completely, no.
Okay, so before you can understand the slit experiments, you have to understand the uncertainty principle. Otherwise, it won't make sense. So the thing to realize with uncertainty is that there are certain state variables that are said to be canonically conjugate, which means that the observation of one of those state variables will affect the state of the other variable. And there are two sets. One is momentum position, and the other one is energy time. And so if you start with momentum position, basically the idea is that, so we have to do a thought experiment. So if you want to measure the distance between two things, how do you do it?
Pull out a tape measure.
All right. Now, what if it's too small to do that with?
So it's magnify it.
Right. And what are we observing when we magnify things?
Things on a micro scale, or
We're observing light, right?
light. Okay, right. Yes, yep.
So do you understand that light is quantized and has individual quanta?
I don't even know what quantized means. What's quantized mean?
It means that light is comprised of a bunch of quanta, which are called photons. So light is not a continuous thing. It is a bunch of tiny little individual light quanta, which are called photons, and together they come together to make what we experience as light. But it's the same as with mass. Like, you can't subdivide light into an arbitrary number of photons. Eventually you get down to just one tiny little photon. So that's what we mean when we say quantized.
Okay.
So are you familiar with that?
So say that sentence again now that I know what quantized means.
Well, light is quantized. So basically, if we want to look at something, we have to send some photons at it, and then we measure the reflected photons.
Right. So that's us. And by doing that, we're actually affecting looking at it, aren't we? Or it's
so the question is, why? You're right, but why?
Well, because we're all connected on a quantum level or something. I don't know.
Because the light possesses energy. And when the photons reach the surface that they're measuring, some of that energy is transmitted into the object that you're measuring.
And vice versa as well? Vice versa? The other way as well?
Yes, it's always bivalent. So what will happen is that the total energy of the photon will decrease because it's transmitted some of its energy into the thing that it was observing, into the thing that it was touching.
Right, yep.
So you're following that so far.
Yep.
So the uncertainty relation gives the relationship between whenever you try to do these really small measurements, there will be a change in the momentum of the system. Because you're measuring a very small distance, there will be a disturbance in the momentum of the system that is under observation, because the energy from the photons perturb the system.
So no matter what, you're affecting the outcome.
So that fact is something to do with quantum mechanics, which is this, what they call the observer effect. So when you're doing an observation, a true observation, there is some sort of disturbance to whatever it is that's being observed. There's no such thing as observation that doesn't interfere with the system being observed. So for example, when you look at something, you're seeing some distortion of what's actually there, right? Because your eyes, what your eyes are collimators. So you can look that up. But the structure of your eye functions as a collimator for photons. So it's not just looking at one thing, it's able to give you a panorama. So even though the eye is very small, it focuses the light to just one tiny little region, right? Which is in your iris.
Yep.
And in so doing is causing a compression to the original light. Because
Right, so it's changing the image as well because it's compressing it.
So the eye is basically absorbing some of the photons.
the eye's observing photons, and there's some type of destruction going on there, right? You're not getting the pure photons, you're getting some compressed version of the photons that are actually in your environment.
Yes.
So this is something philosophically that we have to understand as always happening. Anytime there's an observation, there's some type of waveform reduction. So this example with the eye. Go ahead.
Right, because when we're trying to look at a system that we're trying to test, the fact is that we are part of that system as well. It's almost impossible to be separate from that system that we're trying to measure.
And this is why science is so hard, because we have measurement devices that are compressing information, and we ourselves are compressing information, and we are in some sense part of the same universe that we are attempting to gain some degree of objectivity in, which is ultimately impossible. And it's precisely because of this idea of measurement and waveform reduction being the same thing. So
let's move on to the slit then. So can we move on to that?
That more or less makes sense. You're fine with that on an abstract level, that observation and waveform reduction are the same thing?
Yeah.
Okay. So what is happening with the slit? So we have to first start with understanding what's the actual experiment. You have something that is releasing one electron at a time, right?
Yep.
And you have a slit. And then you have a screen behind the slit. So let's take the slit out of it. What would happen if there was no slit and you just had your little electron gun? What kind of pattern would you see on the screen?
I don't know. I suppose a dot.
You would see one dot that would get brighter over time because each of the new electrons is registering a little bit of energy to the screen, right?
Continually pushing it, it's feeding it. The light is feeding it.
So why is it at that point and not at some other point?
Wait a second. Say that again. So why?
Why do you only observe electrons at one point on the screen?
I don't know. Why?
Okay, so I'm going to explain it again. This is from the perspective of my theory. So if you now go and tell this to a physicist, they're not going to be able to refute it, but they may not agree, right? So just keeping that in mind. The reason is because of something called the least action principle. And this is something in physics. Now I'm now going to apply the least action principle in what may be considered by some to be unorthodox. But because my system basically connects entropy and space-time, I'm able to make more predictions through that connection. So the answer within my system is because an uninterrupted system will flow along what you call an energetic geodesic, which means that the smallest amount of space between the origin and the receiver will be the path that the electron takes. So the electron without the
So the
slit,
path of least resistance, sort of, almost, sort of thing.
you can understand it that way, but basically the electron has to go somewhere, and it will always go to the lowest energy state, and that is the point that is the closest on the screen to the emitter, right? So the electron will, now this is really like, I think it's a self-evident thing, but you have to understand the mechanism so that the other stuff makes sense. It's going to register basically right in front of the emitter. So you'll be able to draw a line from the emitter to the screen and say this is where the electron is going to end up, because anything that isn't that point would represent a deviation from the maximum energy, or sorry, yeah, the maximum minimum energy state, which is the energetic geodesic. So geodesic is, I'll get the actual definition of it because I don't want to.
Why is it important though that you're making a?
It's the shortest. It's the shortest path between two objects. Now I have to call it a geodesic because the configuration of the system will change what the geodesic is.
Okay. Yep. Yep.
So when we have no slit, the geodesic is the trivial one.
Right.
You can just say, yeah, I don't even need to send off one electron. I can already tell you it's going to register right here because that's the closest point on the screen to the emitter.
Yeah. Yeah.
That's fine. And I know it's like, it's much ado about nothing, but this is the way we kind of have to think things through, because otherwise the more complex situations won't make sense. So now we've got that under control. We understand it. Without a slit, it's going to be the boring single point on the screen. Now, what happens when you introduce that slit?
Well, it splits.
What you get is, as you release more and more electrons,
Concentrate. I don't know, sorry.
You get what's called a diffraction pattern. Okay, so if I put a slit there and then I release an electron, before the electron actually makes it to the screen, I have no way of telling you where it's going to end up because there's some degree of randomness to it. Because
that's been placed there.
Because the slit is causing the geodesic to be different. And the mechanism to change the geodesic is this uncertainty principle. So what's happening when you get to the slit is the electron, before it reaches the slit, what kind of shape does it have?
Well, I have no idea, but aren't they circular?
They're spherical.
Spherical, okay, yes.
And how do we know that they're spherical?
I have no idea. How do we know that they're spherical?
We know that they're spherical because the sphere is the energetic geodesic of R3. And that means that...
Of our what, sorry? Of our...
R3, as in three-dimensional space.
Okay.
We live in R3. So R2 would be like a flat surface, R1 would be a line, and R3 is basically what we live in.
Yeah.
Okay, so the geodesic of R3 is a sphere. And the reason for that is because the sphere is the only shape that minimizes the net external torque about the center of mass. So again, that's probably a mouthful, but basically...
Can you say that again, though? Just say that again. Minimizes?
The sphere minimizes the net external torque about the center of mass. So when you blow a bubble, what shape is it?
Well, it's a sphere.
Why?
Because of what you just said.
The answer, and another way to formulate the answer, is that any shape that's not a sphere would require work done on the system. So it's possible to push, like if you take a balloon.
So it's the most optimum thing for...
Right, it's the firmament.
Yeah.
It's the maximum entropy state or the minimum energy state. Those two things are synonymous.
Right.
It's the same with the balloon. So if I blow up a balloon and I tie it off, it's approximately a sphere. But then if I push my finger into it, it's not a sphere anymore because I'm doing work on the system.
Yeah.
That's not a contradiction, because if I take my finger away, what's going to happen?
Going to go back to how it was.
And the reason for that is because there is a shape that is that corresponds to this minimum,
right?
This maximum entropy state. And that's a sphere. So that's, you can actually use that also to like disprove the flat Earth people, right? Which I've done. Ha 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 ha. But anyway,
That's exactly what I was saying. Is it you know, what is the most natural shape? Like water drops. Everything forms a sphere. Like, how do you not understand that?
It's because people don't actually think things through from a foundational level. They can observe things, but they can't see the pattern, right? This is sort of the failure of modern education, is it doesn't teach people enough about pattern recognition. It's just memorizing a bunch of facts. It's not saying this is the underlying mechanism for everything. It's saying memorize this shit, never look for the connections between anything.
Right, or actually learn of what it is, of how it is, you know.
It's not telling you how to think, it's telling you what to think.
Right, it's just just giving you information to regurgitate.
So go on. Can you go
we'll
on?
go back to the slit experiment.
Yeah.
So we've got this electron. We've already proved to ourselves, even though we didn't actually look at the electron, because we know that looking at the electron would actually distort it. We can't look at the electron, but we know it must be a spherical potential because of this energetic quality that the sphere kind of has, that it's sort of the base node, that to deviate from that node requires energy. So we've got this sphere coming along, and what is the slit? It's a teeny tiny little hole that is smaller than the radius of this sphere. So in order to get the diffraction pattern, you can't have a slit of arbitrary size. It has to be sufficiently small. In other words, it has to be smaller than the diameter
of a particle.
It has to be smaller than the diameter of the electron potential function.
Okay.
Because if it's bigger, the electron's just going to go right through it. But if it's smaller, basically you have to imagine like a balloon coming up to a hole that's like half the size of the balloon. And let's say you want to push the balloon through the hole. What's going to happen? You're going to kind of crunch it down, and you're going to modify its overall shape.
Yep.
And that's what's happening when it reaches the slit. So it's not the same as a balloon. What happens when it reaches the slit is it is reduced into one of its eigenstates. So what that means is that before it reaches the slit, the eigenstates for its momentum are still in potential, but overall the momentum is forward. And then when you reach the slit, you have a very small distance that the electron has to go through, and be through the uncertainty principle, distance and momentum are conjugate, which means that a very small distance creates a larger uncertainty in the possible momenta. And so the momentum,
the smaller it is, the more
fanned out it'll be.
Yeah.
Yeah, exactly. And that's something I'm not even sure if the modern scientists can fucking tell you this. So there's a lot of problems in modern science, but yeah, this is what my theory basically predicts. So you can imagine this sphere getting to this little hole and then basically being compressed into a disk that will possess one of several potential velocities, because momentum has an associated velocity, because the classical momentum is mass times velocity. You can look this up. This is standard.
Yeah. Basic science.
So basically what happens is it's reduced into one of its momentum eigenstates, and that will cause it to have a particular velocity that may deviate from straight ahead. And that's why...
Okay, wait. Just before you go, you said into one of its potential eigenstates. What's an eigenstate?
It's hard to explain exactly without a diagram, but basically if you imagine the velocity vector of the electron as being an arrow pointed forward, that's the sort of trivial eigenstate, is it going forward, but on the very micro level, it has momenta going in all directions. So it's a bunch of tiny little arrows.
They're the potential eigenstates. Is that what you're saying?
Yeah, those are in potential. When you get to the slit, that goes from being in potential to being in reality, and then the velocity takes on one of those potential velocities, and that is what changes the direction of the electron. And that's why the electron won't necessarily be registered at the original geodesic, which is that shortest distance. It's going to go somewhere, but this is the thing. We don't know where it will go until it reaches the screen. And this
So
is
What you mean? It can never be predicted?
it can be okay.
the
We do
bounces
that.
off of the other electron from the atoms of the side of the slit, and because the
There's
electrons are moving around so much, whatever it bounces, the angle of it is unpredictable.
There's no interference between electrons. It's just one electron at a time. There's no interference between electrons. It's an interference between the electron and the slit that's causing. It's causing one of those momentum / velocity, because they're the same thing, or they're connected rather. It's causing one of those to become what you call localized, and then the electron now has this new direction that it's traveling in. We can't tell before we do the experiment where the individual electrons will register, but what we can tell is if we do the experiment once, we're going to register a particular distribution of electrons. So that is what I call quantum determinism. We can determine the overall distribution of the electrons, but we cannot determine where individual electrons will be registered. We can only say when we...
So you can see a pattern.
The pattern is deterministic. The individual trajectories are not. And that's why we call it quantum determinism instead of just pure determinism, because this idea of pure determinism has this inbuilt belief that you can know the outcome of any experiment before you actually carry it out, and that's not true. You can only know statistically the outcome. You can't know precisely the outcome for every single electron.
Right. Sort of like a range of possibility.
Yeah, that's why they say that quantum mechanics is statistical. That's what they mean. We can know exactly what the statistical distribution is going to be because we just have to fire out, like, let's say 1 million electrons.
Yeah, so many times.
You'll get a specific pattern, right? And you can know what that pattern is. You can make a graph to represent that pattern, but you can't tell before you do the experiment where one particular electron will go because there's that randomness at the slit. You can't tell which one of its eigenstates it's going to go into. You just know the overall distribution of the eigenstates when you've carried out the experiment enough times.
Okay. So what next then?
Well, that's basically it. And if you want to know
Well,
how the double slit experiment
Yeah,
works,
then you go double slit, yeah.
the way the double slit experiment works is that the basically it's the same idea, except that there's an additional level of interference because the potential might go through both slits at once and then interfere with itself. But it's essentially the same idea.
Yeah, but doesn't it also prove that it can potentially be two states in one, you know?
It can be.
Yeah.
Everything is in a superposition of states. This idea of just having one state is a fallacy. Everything is in a superposition of states. Think of your mind. Think of how many different states your mind has. There's a state in your mind for every single sensation you could possibly have, every single thought you could possibly have. The complexity of your mind is astronomical.
Yeah.
So it's a good example. It's a good question because the slit experiment is sort of the basis for understanding how both observation and uncertainty work. And those things are really foundational to physics. And a lack of understanding of those things will result in a lack of understanding of basically everything else. Okay.
Well, can I ask you this question, right? So you say you're a physicist that's doing the slit experiment, the double slit experiment, the single slit experiment, I suppose. It doesn't really matter, does it? It's the same thing, really, essentially, aren't they? Only one's showing...
The diffraction patterns are different, but the mechanism for the diffraction is the same.
Yeah. And we know that by observing the experiment, we're going to have some kind of effect on it, right? So, you know, say if you were standing in the room doing that experiment, looking at it, you'll have an effect on it. But what if you... No, you won't, because you don't. Your mind has no way of interfering with the machine that's doing the observation. The thing that you're interfering with is the light. That was the point I was going to get to. Yeah. So, but if you were to take the machine that's observing it and replace it with a human, then would you come up with different results? Well, you need to make a hole in the human to register the electron on a screen, and that might be an ethical problem. All right. Okay, so you're talking about that's the interaction of a human. I'm talking more about just observing it, literally standing there and observing it. Wouldn't that affect the outcome of the experiment?
No, because your own consciousness has no way of interfering with the experimental setup. It's not actually observing the experimental setup. It's observing light that's bouncing off the experimental setup that's not interfering with the experiment whatsoever. The experiment.
Okay, then what is it that is observing these experiments that is creating the outcome of the experiment?
The slit is observing the electron, and then the screen is observing the electron.
But they're just things. How can they have an effect if they're just things, sort of thing?
Because that's the nature of our universe. That's why our universe is panpsychic. The observation, the thing that we know as consciousness, the cornerstone of that is observation, and the cornerstone of every single interaction, whether living or not, is also this type of like interaction, and aka waveform reduction, aka observation. Non-living
I get you there.
perform observations. Like the system doesn't need to be conscious the way we are to perform observations. In other words,
it's still there having effect anyway, no matter what.
Well, it's just down to a definition of what is observation, right? Like a lot of people will sort of infer that observation implies that there's an observer, but the observer doesn't have to be conscious. In a lot of cases isn't, because the slit's obviously not conscious in any meaningful way, but it's still performing observation. So that's where panpsychism is tricky, because you have to understand that it's possible for something to do an observation that's not conscious. Because observation is just the act of changing this natural sphere into one of the eigenstates.
So then, because I have no idea, what is it that you've said that is different to what the physicists or quantum mechanics or whatever of this day and age say compared to what you have said? What's the difference? How have you interpreted it differently?
Well, I mean, I'm not the only one to say this. If you look up something called pilot waves, that's very similar to what I've said. So people have like got part of the picture. They just haven't put it together the exact same way that I have. So the main problem with what you call standard model, which is the sort of dominant model of physics, is that it reduces everything down to fundamental particles. And what my model says is that there's actually no such thing as fundamental particles. Everything is a wave. And what we observe as particles are just waves in their maximum entropy state that have collapsed into an apparently solid form. But if you look at it in a very high level of magnification, it's not a true solid.
What is it then? What?
It's a waveform, a very complex waveform.
Like you said, it's just a collapsed waveform.
Yeah, exactly. So when you collapse a waveform enough, it only has 3 dimensions in which it exists. And if all of those dimensions are observed, i.e. through chemical bonds, it will manifest, it will appear to be a solid, but it is not a true solid in the sense of what you would think of a solid as being, which is a continuous object that has a well-defined volume, right? Like that in objective reality isn't real. It only appears to be real because of the scale of magnification that we exist on. Like if you start with an electron, you have to increase that size by, I don't know, it's over 1 billion times just to get to our scale. So we're on a considerably larger scale than the scale of an electron. And for that reason, everything can kind of coalesce into things that appear to be solid, even though we know through science a true solid in the sense of a continuous object doesn't exist.
But so that's you're implying that we are then in a simulation or a living in a hologram or something.
Yeah, well, if you want to think of all these waveforms as being holograms, you can. That's an aesthetic preference, and there's nothing wrong with that. It's not false. Not everyone's going to agree with you, but if that's what floats your boat, then it's not wrong.
What would you call it then? So what would you call it?
I would say we live in a fractalized universe, which has a measurement limit of 3 + 1, 3 space and 1 time like dimension, which are maximally entangled on the micro scale and maximally disentangled on the macro scale.
And when you say entangled, what are you meaning?
I mean that space and time are entangled on the micro scale to a considerably larger degree. And I'll get a diagram because I don't think it's going to make sense without a diagram. So let's talk about our scale. Can you accept that we have 3 space-like and 1 time-like dimension?
Well, where we are at the moment, yeah.
So you're basically fine with that. Do you think that the space and time dimensions we experience are interrelated?
Time and space, are they interrelated?
Yeah, there's no wrong answer. I'm just trying
I'm
to...
just trying to... Well, I think they are interrelated, yeah.
How?
Yeah. I don't know how.
There is a periodicity to space, i.e., we experience a day where everything is essentially repeating on a 24-hour time scale. Yeah. And then it's also repeating on a 365 or 4 or whatever on a yearly basis, right?
Yeah.
So depending on what level of if you stay on the level of the planet, the period, i.e. the amount of time it takes for the space to go back to the original configuration, is 24 hours. But then if you pull back to the order of the solar system, the period becomes 1 year, right? Because that's how long it takes for the Earth to go around the sun.
Mm-hmm.
So this is what people mean when they say that time is not linear. It's cyclic.
Wait a sec. I just wanted to stop you there. Like you said, oh God, my head. Was it you said, well, if you said you would come back to the same point in space again, right? When you said it takes 24 hours, we come back to the same point in space again.
Relative to ourselves, not relative to the greater universe, because there is no true.
Okay, right.
There is.
Yeah. Right.
Everything is relative to where you're measuring it from. So we can say there's a periodicity of a day, and we can say there's a periodicity of a year. Those two things are not a contradiction. They're true on different scales, right?
Yep. Okay.
So this is what
I was going to go, because we're not actually coming back to that same place again. It's like you said, it's a period thing, not a you said, it's relative to me personally rather than the universe at large.
What I'm trying to get you to understand is that there is a connection between space and time, even on our scale. It's just not very close. I mean, for all intents and purposes, when you're like sitting there, it doesn't really feel like there's any obvious connection between space and time. Space is one thing and time is something else, right? Space is the thing moving through time. But then if you look at it the way I just explained it, with the periodicity of the rotation, you realize, okay, space and time have to be connected somehow. When we look at it through that lens, it's very obvious there is some connection. It's just not that closely, it's not that much of a connection, because we can kind of convince ourselves when we're not looking at things on the scale of a day that space and time are what you call orthogonal.
So the smaller we look at the smaller we look down into things, is that the more that space and time seem separated? And then
no, it's the more they're entangled. So if you click on my,
the more they're entangled.
If you click on my icon right now.
Oh wait. Oh yeah, no, it's up.
So
I had a good look at this before.
So this is the shape of the quantum periodic table, and I'll show you why it is also satisfying the 3 + 1 So on our scale, 3 + 1, you're fine with that. 3 space, 1 time.
Yeah.
On this scale, which is extremely teensy, it's the smallest scale you can get. There is nothing smaller than the scale of an atom. On this scale, space and time are what you call maximally entangled. And so you have 1 and then 2, because these two things here are, even though there's 2 of them, they're the same size. So
Yep.
we've got 1, 2, 3, 4. Same as what we have here, except it manifests differently because they're literally twisted up together. So the space and the
So that's why they don't. That's why they're not symmetrical, or they don't match up on either side. You've got different balls. Is that what you're meaning?
They're symmetric about the origin. So if you
Yes.
start, they're not. So normally when we think of symmetry, it's about the y-axis, which would be a line drawn from the top to the bottom. But this diagram here is symmetric about the origin. So if I go from the origin out to the first blue ball on the left, it's the same distance to the first blue ball on the right.
Yeah.
And that's why I have those R's in there, because they're representing this fundamental attribute of the universe that's true on all scales, but manifests differently on all scales, of what I call the measurement limit, which is this idea of there being 3 + 1. I don't know what to call them exactly, but I guess you could call them 3 + 1 space time somethings. But anyway,
3 + 1ers.
I invented this myself, so I don't have the right words for it. I'm trying to come up with words that'll be easy for people to understand. So it is good for me to answer these questions because it helps me develop the theory a little bit better. But coming back to this idea of, it might be sort of curious as to why appears to be a dualism, i.e. there's only, if you look at the periodic table, are you familiar with chemistry at all?
Yeah, but it's years ago. But I mean, I've seen the periodic table recently because of my kids and everything.
Do you know what cardinality means?
No, I remember learning it, but I have no idea now.
Okay, cardinality means the number of elements in a set. And if you look at the periodic table, there's only 4 cardinalities of periods. So the first period has 2 elements in it. The next period has 8. The one after that has 8. The 2 ones after that have the same number, and then the 2 ones after that have the same number. So again, you have a cardinality of 4. There are 4 different numbers of elements per period. And this duality, i.e. there being 2 rows with the same number of elements in them, is basically the same reason that our bodies are symmetric. So we are sort of resorbing that duality into our body, which is why we only experience 3 + 1 or 3 physical dimensions on the scale, as opposed to the periodic table, which has 7 different periods.
But how do they? But how is the periodic table periods related to us?
Because we're all space-time events. You are a space-time event, albeit enormously more complex than the periodic table. You yourself.
Okay. You're talking on a chemical level. Then you're talking on chemical level.
It's more of a quantum level.
All right. Yeah, I don't know. Something well, go on. Just go on, as you're saying.
So this is another diagram. So this is another diagram I made. I don't know if you can see it, but basically it's a 2-dimensional painting of the periodic table that I did. And then I've got this guy underneath it to sort of show the similarities between this fundamental, what you call the micro-canonical space-time event. That's what the periodic table is. And we would be macro-canonical space-time events. So we would have similarities between the periodic table and ourselves, but it's obvious that we're quite a bit more complex. But we still have a symmetry.
Sorry, go on.
We have a symmetry to us. We have this duality, like we have 2 eyes. You can draw a line through the body and have it be approximately symmetrical, but not perfectly symmetrical. Obviously, I get that.
So you're talking now about the Fibonacci sequence. It's the code that's sort of fundamentally
Yeah,
within
there is a
everything
code.
on Earth.
There is a natural, what I call a natural geometry.
Right. So not say
This is an aesthetic preference. Some people, like Rufus, will always have an aversion to the idea of something sacred because they're averse to religion, right? So it's, I mean, if you want to call it sacred geometry, you can. It's just not everyone's going to agree with you, right? And that's fine.
Oh, I was just, yeah, what I was asking is whether you're talking about this. It's the same thing you're talking about. They're idiots then.
I'm fine to call it sacred geometry. I have no aversion to religion.
Yeah, right. Yeah. But whatever you call it, whatever you choose to call it, I suppose. But yeah, it's just, yeah, so that's, well, then the next question for me is why do you, well, how is it that on a fundamental level and then on a macro scale, we're all basically written with this code? Everything is written with the same code, everything on Earth.
Because we live in a fucking amazing universe and it's beautiful.
Okay, well, that's what I like to say because it's just beautiful, but it almost feels like I want more answers to that.
There is no answer to that question.
I know, but it's a question. It's an answer that you want.
The fact that we can tell this stuff is an indication of just how amazing it is to be human.
Yep, I agree. Yep.
But in terms of what you want to call it, I mean, it's always just going to be an aesthetic preference.
Yep.
It doesn't have a name. That's why I say the eternal religion has no name, because you can't put a name on something like that, because whenever you do, you're you're observing it, so you're compressing it. So you're not giving the full answer.
Yep. Yep.
God damn, I love science.
Well, thanks for that.
You're welcome. I'm glad you asked the question, because not enough people ask that question, and it's an important one. And I'm glad I got a chance to talk about it, because every time I get a chance to explain it, I get a little bit better. And I'm sure I'm actually not doing that good of a job right now because I haven't had enough practice. But over time,
well,
I'll be
I asked it
even more. It's hard to explain.
I've been listening to you for a couple of weeks and I haven't heard anyone ask it. So I thought it's about time you know, people actually heard what the basis of what you're talking about is.
I think most people just don't have the words to actually even ask the question, because they wouldn't know what they were asking.
But it's pretty fundamental as to understanding what you're talking about, Jen.
Well, that's why some of the knowledge is kept secret, because you have to be able to ask the right questions before the answers can mean anything.
True, but I'm not going to say eye to eye on that one. I just think, I don't know, fundamentally inside me as a Libran, and I'm not really into the stars, but I think all truth should be out there, and then we've got to deal with however we deal with it. But that's just my fundamental.
Well, I'm confident that as you learn more, you'll change your mind.
I'm confident I won't.
You don't know what the hidden knowledge is.
What was that? Sorry? What did you say then, sorry?
You don't know what the hidden knowledge is.
Oh, I can't know. It's hidden knowledge.
So that's what I'm saying. If you knew, you would understand why it's hidden.
Okay. Yeah.
Like, for example, there's techniques where you can stun paralyze someone's mind. Would you want somebody who was a complete shitbag to be able to access that type of technology?
Well, no, I wouldn't. But what I would say is that technology is probably already in the hands of the worst shitbags on Earth anyway.
I know. That's why I'm doxing so much of this information, and some people might be very pissed that I'm doing it, but I feel that if I don't do it, we might lose it entirely, and that would be far worse than, keeping it, you know what I mean? Losing it would be worse than it being misapplied.
Yeah, I know what you mean. Yeah.
That's the dilemma I face every day, because I have a community of masters that I have to answer to, because it's part of tradition to be part of a community of masters, and they might not like what I'm doing because they're not going to like that their secrets are being revealed, or it's being revealed that they didn't even know this stuff.
doesn't sound
But
like a
that's
very. That
karma.
doesn't sound like a very wise bunch of bastards to me.
Well, that's just, I mean, people are a product of their environment. That they are the way that they are because of the tradition that they come from. They have that knowledge because they've kept it secret in a lot of ways.
Yeah. Doesn't justify it though.
I'm sure you're not who feels that way. I mean, a lot of people wanted this knowledge to the point that they were willing to kill for it, and they did, and they got it. But as you can see, they're not using it the right way. They're using it for selfish purposes. They're not using it benevolently.
Yeah. Well, I'd agree with you there.
So basically, we have to
Sorry.
attack them. We have to attack them, and we have to disable them. And the only way to do that is to get those abilities ourselves. We have to fight. We have to fight fire with fire, essentially. And we're at a state right now where most people don't have any ability to use this stuff. So what I'm trying to do is get some people, the right people, up to a point where they can oppose the people who are misusing it, because they'll have essentially more power than they do because they're doing it for a more benevolent reason.
For the right reason.
Well, a more correct reason, a better reason, not a perfect reason, but a better reason.
Okay, yeah, which is a good thing to recognise, I suppose, because if you say it's not perfect, it means you can be prepared to change it in the future.
If you think you're perfect, if you think you know everything, you're basically fucked. Well, look at Claire. She's a perfect example. She literally thinks she knows better than everybody, and she's totally fucked. And she can't change her mind. She's a prisoner of her own beliefs. And that's why these false beliefs are their own punishment, because you get trapped in a prison of your own making. You think you know everything, and therefore you are unable to learn anything.
Good point. Yeah, that's a good point. Never heard it put like that.
So that's basically what we're up against right now, is people who think that they know everything, people who think that they know better, and people who think that they should have basically a monopoly on these techniques. And I disagree. And some people might disagree with me, but I'll deal with them when the time comes. Because I'm not willing to risk losing all this knowledge just because of some stuffy fucking traditionalist who was, too proud to fight back against these bastards. But I mean, it's tough for me because I'm getting it on both ends. Like, I'm getting it on the end of the traditionalists who are pissed that I'm going against tradition, and I'm getting it on the end of you guys who are saying, well, why can't you just tell me everything? And so it's really tough line to walk.
Okay, well, I can hear you there, Jim. I hear you. I guess, like you said, you don't know until you know.
Well, that's why I'm doing what I'm doing, is so that I can meet people like you and people like Zero who might be able to use these techniques in a better way.
Okay. Zero, you were jumping in a couple of times then, but I didn't hear what you had to say. Now, probably past his bedtime. It's getting late over there, isn't it? Have you been looking at the chat, Jen? Let me have a look. Am I on silent? Hello?
Mm-hmm.
Oh, good on it.
I think it was like 1960s where all the secret societies have decided to all the books basically are to be available for everyone. And even back 100 years ago, Madame Blavatsky, she's the one who sort of stated that some of this knowledge has to come out So there's some sort of a move between all the mystery schools and so forth to begin to give this knowledge to humanity, because they're barely becoming ready to handle this knowledge.
Yeah, and I'm stuck cleaning up her fucking mess. Look at how much that stuff's been abused.
Right.
So without an actual reverence for the traditional teachings, it's going to be abused. And she abused those teachings. She was not reverent enough of the origin and the tradition. So it was inevitable that she was going to misuse them. And now look at the disaster that we're in, where nobody has any respect for tradition. Nobody has any respect for anything. Everybody thinks that they're entitled to whatever the hell they want. And we're all basically spiritually degenerate.
Oh, I just jumped in and had a look at the chat and I can't stop laughing.
Are they chimping out again?
No. I shouldn't have looked. I'm going to turn the fucking thing off.
Chimping out? What does that even mean?
I might take the dog for a walk, guys. So I'll see. Maybe come back a bit later if it's still going. We'll see you later. Thanks for that, Jen. It was interesting.
You're welcome. Talk to you later.
See you, Zero.
Later.
Just quickly, they keep on talking about Conan. Is it true that Conan's under 18? I thought he was a grown man. Anyway, see ya.
I'm trying to can't find the group. It's like kind of hanging out the window and then it's not there.